Hello, good morning everyone. How is everybody doing? I hope you are good despite the circumstances that we are facing right now. To start today's episode, I have some few reminders. If you are using earphones or headphones with high volume, please don't do it. Did you know that if the volume is at the maximum level or approximately 100 decibels, in 30 minutes it can affect our hearing? And we call it noise-induced hearing loss. So you're advised to listen to this podcast at low volume. There you are now ready to begin. Hello Kasensya, it's me, Rowie Azucena, your companion to your Wonder Science adventures. So buckle up and get ready to power your mind. To start, draw your attention to these few questions. The first one is, it is the deepest oceanic trench on Earth, where it is crescent-shaped and measures about 2,550 km in length and 69 km in width. If you say Mariana Trench, then you are correct. What about this one? The most well-known reef valley on Earth, which stretches from the Middle East in the north to the Mozambique in the south. If you are thinking about the Great Rift Valley, you are absolutely right. In some ways, our planet Earth resembles a giant jigsaw puzzle. Why do you think so? That is because the Earth's outer surface is composed of tectonic plates, which are innermost section of the planet's crust that roughly fit together and meet at the places called plate boundaries. For today's episode, we will explore the different types of plate boundaries. Kasensya, let's begin. Plate boundaries are the lines at the edges of the different pieces of the lithosphere. And the lithosphere plates are moving due to the convection current in Earth's interior. There are two types of crust. The first one is continental crust, which is thicker but less dense. And the second one is the oceanic crust, which is thinner and denser. Remember, the Earth's lithosphere moves slowly and constantly over time. It rides on a warmer, softer layer of the mantle called the asthenosphere. This movement causes the formation of plate boundaries, namely divergent, convergent, and transfer fault plate boundaries.
Good day everyone, my name is Martes Gazingan together with my partner Josamita Gayon. We are here to discuss about the first kind of plate tectonics, which is convergent plate boundary. We will be discussing the definition and explore the features, interesting facts, and the real-world examples of convergent boundary.
Before we start, let me ask you a question. What is a convergent boundary? Imagine the world is like an egg with a shell that is cracked all over. Imagine holding a cracked pieces of eggshells. The entire outer crust of the earth is broken down into sections. This is what we call tectonic plates. But instead of resting on a liquidy egg yolk, the plates float on a sea of hot magma, something you'd only actually see in rare events like volcanoes. This magma is not a liquid, it's actually a solid. But under the incredible pressures beneath the Earth's crust, even solid flow like a hot.
The cracks in the egg are boundaries between plates. A convergent boundary or destructive boundary is where two plates are moving towards each other and colliding. The pressure and friction is great enough at these boundaries that the material in the Earth's mantle can melt and both earthquakes and volcanoes happen nearby.
Let's move on to the features of convergent boundaries. When two plates meet, one inevitably gives way and sinks below the other. This is what we call subduction. The subduction zone is the area where two plates are sandwiched on top each other, like a tectonic. Exactly what happens during the subduction depends on the type of tectonic plates involved. There are three types of plates. These are the oceanic continental, and continental convergent boundary.
So the first type of convergent boundary is the oceanic convergent boundary, where different oceanic plates run into each other. The older and therefore cooler and denser one dives beneath the other. In other words, it subducts. Such a convergent boundary includes a seafloor trench marking the earthquake-rattled subduction zone, as well as an island part, a line of volcanoes created by rock melt in the mantle associated with subduction. Other features of oceanic convergent boundary are the fore-arc basin between the trench and the island arc, and the back-arc basin on the opposite side of the arc. An example of an oceanic convergent boundary is that between the Pacific and Mariana Plates, which includes the Mariana Islands arc and a subduction zone encompassing the Mariana Trench, the deepest part of the world ocean. The world ocean is the name for the collective group of oceans on the planet.
Next type of convergent boundary is the oceanic continental convergent boundaries. Where oceanic and continental plates collide, the former subducts beneath the latter because ocean crust rich in iron and magnesium. It is also denser than continental rock. Here again, a subduction zone occurs, as does a volcanic arc that develops on the continental side of the boundary. In between, sediments slough up against a continental margin, form an accretionary wedge. This is an example of an oceanic continental convergent boundary. These are the collision of the India plate with the Eurasian plate, creating the Himalaya mountains, and the collision of the African plate with the Eurasian plate, creating the series of ranges from the Alps in Europe to the Zagros Mountains in Iran.
Then the last type is the continental convergent boundary. Convergent boundary between continental plates are a bit different than oceanic and oceanic continental mashups. Continental lithosphere is too buoyant to subduct deeply. So rather than a subduction zone and trench, these boundaries encompass a thick mess of folded filled top crust. This compression results in massive mountain belts rather than the volcanic arcs powered by subduction zone magma in the other two cases. The classic example of a continental convergent boundary is the rumpled overlap where the Indian plate drives into the Eurasian plate, a tectonic collision that has thrown up the greatest mountain in the world, the Himalayas, as well as the vast high Tibetan plateau. To the west, the Alps grew in similar fashion via the collision of the African and Eurasian plates.
These are the examples of convergent boundaries. The west coast of South America is a convergent boundary between the Nazca Plate and the South American Plate. The collision of the oceanic and continental plate was how the Andes Mountains were formed.
Convergent boundaries can also form islands. The northern part of the Pacific Plate is subducting under the North American Plate, and the result is the formation of the Aleutian Islands.
So now, let's have a recap of our discussion. A convergent boundary or destructive boundary is where two plates are moving towards each other and colliding. When continental plates collide, the impact is so significant that the material in the subduction zone is pushed upwards. This is how mountain ranges forms, including even the biggest ones in the world like the Himalayas.
When one oceanic and one continental plate meet, the denser oceanic plate subducts under the less dense continental plate. This forms a trench on the oceanic side and volcanoes and mountains on the continental side. When two oceanic plates meet, they form large trenches underwater. Material that is liquefied under the pressure is pushed upwards, forming underwater volcanoes which create an island.
Good day everyone! This is again another episode of the Plate Boundaries, a trilogy series. Now plate boundaries has something to do with the mechanism of the fault lines and how they move and what are the consequences of these movements of the plates. But then, I am Terry Morimifa Jr. together with Miss Erica Benyes, pleased to guide you to the journey of the plate boundaries. Now last episode, Miss Tagayun and Miss Kasingan discussed to us all about a type of plate boundary which is the convergent plate boundary. Now this time, we will explore another type of plate boundary, the opposite of the aforementioned plate movement, which is the divergent plate boundary.
So what is all about divergent plate boundary? Okay, from its keyword, divergent. I know this is a familiar word to you, sort of a name in the movie. Yes, it is. But here's the catch. Divergent is all about moving away from each other. Now, in the case of a plate boundary, plates are now moving away from each other. Wow! Like some sort of continental drift, right? You know those pockets of landmass drifting away from each other in the movie of Ice Age series.
Now why is it that these large plates move apart from each other? Well, we believe that the major mechanism for this is the upwelling of the convection currents within the mantle. There appears to be a large convection currents takes place in the upper mantle. In places, these convection currents arising hit the lithosphere and move from side to side. As a result, there is a huge force that is trying to spread the lithosphere above apart. This motion now thins the lithosphere and eventually the lithosphere above the mantle breaks and pulls apart. The convection current also causes the plate material above to be dragged along in the direction of the flow as the plates drift, and therefore the drag material now fills the gap on the either side. So this diverging movement gave its name divergent plate boundary.
Now, whenever you take slabs of rock and you pull them apart, the rock will eventually break under the strain and form normal faults. So divergent plate boundaries are characterized by lots of normal faults, many of them running parallel to each other with the blocks of rock between them dropping to form these fissures, which will eventually thin the crust right down to 5 to 10 kilometers thick. That is all what is happening deep down. But what about in the surface? What features can we see along this type of boundaries?
When a divergent boundary occurs beneath a thick continental plate, the pull apart is not vigorous enough to create a single break through thick plate material. Here, the thick continental plate is arched upwards from the convection current's lift, pulled in by extensional forces, and fractured into a rift-shaped structure. As the two plates pull apart, normal faults develop on both sides of the reef, and the central blocks slide downwards. Earthquakes occur as a result of this fracturing and movement. Early in the reef-forming process, streams and rivers will flow into the sinking reef valley to form a long linear link. As the reef grows deeper, it might drop below sea level, allowing ocean waters to flow in. This will produce a narrow, shallow sea within the reef. Now this reef can then grow deeper and wider. If the rifting continues, a new ocean basin could be produced. Now there are the effects that are found at this type of plate boundary, which includes a reef valley that sometimes occupied by long linear lakes or a shallow arm of the ocean, numerous normal faults bounding a central reef valley, and a shallow earthquake activity along the normal faults. Volcanic activity sometimes occurs within the reef. A classic example of this type of plate boundary overlying a continental plate is the East Africa Rift Valley. The East Africa Rift Valley is in its very early stage of development. The plate has not been completely rifted, and the rift valley is still above sea level but occupied by lakes at several locations. However, the Red Sea is an example of a more completely developed rift. There are the plates that have fully separated, and the central rift valley has already dropped down below the sea level.
Now, what if a divergent boundary occurs under an oceanic plate? When a divergent boundary occurs beneath oceanic lithosphere, the rising convection current below lifts the lithosphere, producing a mid-ocean ridge. Extensional forces stretch the lithosphere and produce a deep fissure. When the fissure opens, pressure is reduced on the superheated mantle material below. It responds by melting, and the new magma flows into the fissure. The magma then solidifies, and the process repeats itself. Effects that are found at a divergent boundary between oceanic plates include a submarine mountain range such as the Mid-Atlantic Ridge, volcanic activity in the form of fissure eruptions, shallow earthquake activity, creation of the seafloor, and a widening ocean basin. The Mid-Atlantic Ridge is a classic example of this type of plate boundary. The ridge is a high area compared to the surrounding seafloor because of the lift from the convection current below. In relation to our lives, sometimes breaking apart creates a new beginning. Like in the oceanic case, when two plates move apart from each other, new material coming beneath the Earth's surface appears and filling the gap between the two. Thus, creation of the new seafloor and widening ocean basin. Sometimes, when things cannot be mended by staying, it might be resolved through departing. Maybe a fresh start to get things forward and a break away from the past. Maybe you are not well suited for each other. That's why feelings grew fainter, making the two of you moving away from each other. Despite numerous dialogues, it does not resolve the issue. Hence, breaking away will be the last resort to solve the issue and move on.
Now time to recap. So divergent plate boundaries are locations where two plates are moving away from each other and a new crust is forming from magma that rises to the Earth's surface between the two plates. It is caused by these convection currents causing the movement to pull apart the crust and creates rift valley when an overlying plate is continental plate and oceanic ridges when the overlying plate is an oceanic plate. These movements allowed us to understand how geographical features in the natural world were created. This will clarify us that the Earth is indeed a changing planet, a mystery to solve as its natural wonders unravel the beauty behind the massive forces that is occurring inside our humble abode.
Good day everyone, this is again another episode of the Plate Boundaries. In some ways, Earth resembles a giant jigsaw puzzle. That is because its outer surface is composed of about 20 tectonic plates, enormous sections of Earth's crust that roughly fit together and meet at places called plate boundaries. I am Vincent Kennedy Dante together with my partner Kyle Ryan Villaspin. This time, we will delve and go deeper on transform plate boundary.
Thank you for that wonderful introduction, Vincent. Hi everyone, I'm Vincent's partner, Kyle Ryan CVSP, discussing transform plate boundary. But before that, we have some questions for everyone who is now listening. So my first question is, what is all about this transform plate boundary? So, transform plate boundary occurs when two plates slides past each other horizontally. Interestingly, a well-known transform plate boundary is the San Andreas Fault, which is responsible for many of California's earthquakes. It connects the East Pacific Rise, a divergent zone to the south, with the South Gorda Juan de Fuca plate, a smaller, older plate consisting of all three boundary types, and Explorer Ridge to the north. Viewed from the air, the fault line is represented by a linear, shallow trough. From the ground, the fault line can be identified by several characteristic landform, including long straight escarpment, narrow ridges, and small ponds formed by settling. So now, the transform plate boundary mechanism. Take note that this fault is generally our focused areas of deformation or strain, which are the response of build-up stress in the form of compression, tension, or shear stress in the rock, at the surface or deep in the Earth's subsurface. Transform faults specifically accommodate lateral strain by transferring displacement between mid-ocean ridges or subduction zones. They also act as the plane of weakness, which may result in splitting in rift zones.
First, why is it called a transform boundary? Along the third type of plate boundary, two plates move laterally and pass each other along a giant fractures in Earth's crust. Transform faults are so named because they are linked to other types of plate boundaries. The majority of transform faults link the opposite segments of oceanic ridges.
For the next one, what landforms are formed at the transform boundary? So, transform boundaries represent the borders found in the fractured piece of the Earth's crust, where one tectonic plate slides past another to create an earthquake fault zone. Linear valleys, small ponds, stream beds split in half, deep trenches, and scarps and ridges often mark the location of a transform boundary. The San Andreas Fault, a transform boundary extended 750 miles from the Californian-Mexican border through San Francisco, where it runs along the coastline before dodging out to sea near Eureka, California.
What features are found at transform boundaries? Transform boundaries are marked in some places by linear valleys along the boundary where rock has been ground up by the sliding. In other places, transform boundaries are marked by features like stream beds that have been split in half and the two halves have moved in opposite directions.
Finally, the last question for this episode, what happens at a oceanic transform boundary? The grinding action between the plates at the transform plate boundary result in a shallow earthquake, large lateral displacement of rock, and a broad zone of crustal deformation. Perhaps nowhere on Earth is such a landscape more dramatically displaced than along the San Andreas Fault in Western California. So with this, Vincent, my partner, have a few things to add about the transform fault boundary. Now I will pass on the mic to you, Sir Vincent.
Now, time to recapitulate. Transform faults are commonly found linking segments of divergent boundaries. These are the mid-oceanic ridge or spreading centers. These mid-oceanic ridges are where new seafloor is constantly created through the upwelling of new basaltic magma. With new seafloor being pushed and pulled out, the older seafloor slowly slides away from the mid-oceanic ridge toward the continents, although separated only by tens of kilometers. This separation between segments of the ridge causes portions of the seafloor to push past each other in opposite directions. This lateral movement of seafloors past each other is where transform faults are currently active. Transform faults move differently from a strike-slip fault at the mid-oceanic ridge. Instead of the ridge moving away from each other, as they do in other strike-slip faults, transform fault ridge remain in the same fixed locations, and the new ocean seafloor created at the ridge is pushed away from the ridge. Evidence of this motion can be found in paleomagnetic stripping on the seafloor. A paper written by geophysicist Taras Geria theorizes that the creation of the transform faults between the ridge of the mid-oceanic ridge is attributed to rotated and stretched sections of the mid-oceanic ridge. This occurs over a long period of time, with the spreading center or ridge slowly deforming from a straight line to a curved line. Finally, fracturing along these planes forms transform faults. As this takes place, the fault changes from a normal fault with extensional stress to a strike-slip fault with lateral stress. In this study done by Bonatti and Crane, peridotite and gabbro rocks were discovered in the edge of the transform ridge. These rocks are created deep inside the Earth's mantle and then rapidly exhumed to the surface. This evidence helps to prove that the new seafloor is being created at the mid-oceanic ridge and further supports the theory of plate tectonics. Active transform faults are between two tectonic structures or faults. Fracture zones represent the previously active transform fault lines, which have since passed the active transform zone and are being pushed toward the continents. This elevated ridge on the ocean floor can be traced for hundreds of miles and in some cases even from one continent across an ocean to the other continent.
And that ends our episode for today. Remember our three types of plate boundaries? The first one is divergent boundary, where new crust is generated as the plates pull away from each other. The second one is convergent boundary, where crust is destroyed as one plate dives under another. The third one is transform fault boundaries, where crust is neither produced nor destroyed as the plates slide horizontally past each other. Okay, I hope you understand something today. Again, I'm Roby Azucena saying, science is fun for everyone.